I wanted to show you another example where we find the area of some region bounded by curves here. In this case, I've got two functions, f of x and g of x. One's a cubic polynomial, 3x cubed minus x squared minus 10x, and the other, g of x, is a quadratic. Right? So I want you to start thinking about what those two functions look like, whether it's either separately or together. But we're going to probably want a graph of these two functions to hopefully then be able to visualize the area of this region that we're looking at. And that's all I have. I've got two curves, is it. So what I'm assuming is that these two curves are going to kind of close in some area together. Okay? So what I want to work towards here is finding a graph. I want to find a graph of these two guys. And like I said, if they work together to close in some area, then their intersection points are going to be a place that we want to look. And that, in fact, will probably give us our bounds of integration. Right? So these two things together will likely give us our bounds. Okay? I find the intersection points by setting these two functions equal. So 3x cubed minus x squared minus 10x equals minus x squared plus 2x. And I move all the x's to one side, right? That leaves me with a 3x cubed minus 12x equals 0. And I'm going to factor and solve that cubic equation, right? And I see a 3x in common between both 3x cubed and minus 12x. So I pull a 3x out. I have an x squared minus 4 left over, and that leaves me with 3 intersection points when x is 0 and plus or minus 2. So these two curves are going to intersect with each other 3 times. Okay, I'm not sure exactly what that looks like just yet. We'll show that here soon. Another interesting or another useful bit of information I could extract from these is the x-intercepts, or just the intercepts in general, x and y. And that's also going to help me graph these two functions. Okay, so if I don't have an online tool, if I don't have a calculator, I can still use what I know about cubics and quadratics and their intercepts and intersection points to then find a picture of what's going on. So if I look at the x-intercepts of f of x, I want to try to solve the cubic equation of f of x equals 0. I've already factored out an x there because there's an x in common of each of the 3 terms. And then I want to try to factor 3x squared minus x minus 10. Okay, and I can factor that. If I break apart that minus x in the middle into like a minus 6x plus 5x, I'm able to then factor and use some grouping to determine that that quadratic is going to factor to 3x plus 5 times x minus 2. That should give me my whole function f there. When I set that equal to 0, I get 3 x-intercepts, 0, negative 5/3, and 2. Okay, so those are going to show up as when f crosses the x-axis. And I can quickly do the same with g. Minus x squared plus 2x equals 0. This one's a bit easier, solving that quadratic equation, minus x times x minus 2. So 0 and 2, which also happen to be intersection points of the two curves, 0 and 2 are the two places, the two x values where g is going to cross the x-axis. Okay, so let's put all this information together into a picture. If you need to pause here and make sure you've got everything copied down, I'm going to give you a graph. Here's f and g together, and I'm going to try to describe that information we just found and that it makes sense based on what we were working with the intercepts and things like that, and how it corresponds to our picture here. So right now I've got f colored in green. I'm going to change that so that it makes sense with the previous slide, and G colored in purple. So first, what I do is I see that these two kind of enclosed areas are what we're looking at for the area between these two curves, those two enclosed regions, right? I can kind of assume that it's not, say, this up here, because that's not enclosed, right? It's just open. It's not boxed in at all. So anything that's enclosed is the area that I'm looking for, okay? So again, I'm going to color F to be pink and G to be orange. And I've got this here. Now I've also colored in red their intersection points. So again, I just want the colors to match to the previous page. Those red points are the first 3 points, the first 3 x values I found, they're intersection points. I didn't find the y values, I just found the x values of -2, 0, and +2, okay? I also found the x-intercepts, and that's just to make sure that what I found makes sense to the graph. The x-intercepts of f are in pink there, same color as the function, at -5/3, right? That's just a little bit, more than -2, right? It's to the right of -2, 0 and 2. And then the x-intercepts of g, that orange function there, are just 0 and 2. So I've colored over those again. We see a lot of redundancy in those points. But basically, I'm just trying to argue that the information I found before makes sense to what these functions look like. You can also talk about how f is a cubic and how its end behavior is. One end should open up downwards and the other should open up upwards. The quadratic opens downwards because there's a negative in front of the x squared, those sorts of things. So we can use all of that information to describe a picture. I want to find the area, okay? So what I want to pay attention to is that in the interval from -2 to 0, which function is larger, which is on the top, right? So I know that my integral formula that gives me area, f has to be bigger than g, okay? I know that doesn't hold true all the time, so that's why I write it or think about it like top minus bottom. So from -2 to 0, -2 to 0, f is bigger than g. The pink function is larger than the orange function, right? F is bigger than g. So in that integral, f should be first, and I should subtract g from it. Same idea, but backwards from 0 to 2, there, g is bigger than f. So I've actually got 2 separate integrals here that's going to give me the total combined area when I add them together. So I've got 2 areas, A1 and A2. Let's find A1. That's the place where f is bigger than g. Okay, so the integral should be from -2 to 0 of f minus g dx. That's basically exactly how we learned that basic formula, f minus g. It's top minus bottom because f is bigger than g. A2 is kind of backwards of the formula. From 0 to 2, g minus f, because g is larger than f on that interval. Okay, so what I do then is I add the 2 integrals together in order to find the total combined area, A1 plus A2. Okay, I'm going to write these both down in their full integral form. So here we go. A1, that integral there, f is that cubic, minus g is the quadratic, dx, plus the second integral is the quadratic minus the cubic, dx. Okay, I actually forgot a parenthesis. Let me put that in there. I should have another closing parenthesis. Okay, that is the total combined area, and it's in the form of 2 integrals, top minus bottom. Okay, let's go through that. I'm going to simplify the integrands of each one. I see quickly that I will have x squareds disappear, minus x squared minus a negative x squared in the first. In the second, I'm going to have a minus x squared minus a negative x squared again. So those are both going to go away. I'm going to jump slides here. So what I should have is something like this. The total combined area are the 2 integrals from -2 to 0. The integrands will simplify to 3x cubed minus 12x. Then the second integrand should be 12x minus 3x squared. So take some time and make sure you understand where those parts come from. I'm just going to now antiderive, find the antiderivatives, use the fundamental theorem of calculus, and plug in those numbers. Okay, so the antiderivative, that first integral becomes 3/4 x to the 4th minus 6x squared, evaluated from -2 to 0, plus that second integral is going to give me a 6x squared minus 3/4 x to the fourth. Okay, when I evaluate that first integral, or that first antiderivative at the upper limit of integration, that 0, I don't really get anything, right? Because each x, or each term, has an x. So that's 0 minus what I get when I plug in -2. Plug in -2, I get -2 to the fourth is 16, -2 squared is 4. I'll crunch those numbers in a second. Plus, what I get in the second integral, when I plug in 2, I should see a 6 times 4 minus 3/4 times 16. And again, plugging in 0 doesn't give me anything useful. So I'm ready to crunch these numbers. I've got negative outside of that first parenthesis there. I need to pay attention to this negative sign here. 3/4 times 16 should give me a 12, and it's negative, minus 24, and that's also negative. So it's -12 plus 24, minus a minus. I've got to distribute that minus sign. And the second integral is just kind of how I read it, 24 minus 12. All said and done, 24 minus 12 plus 24 minus 12 is 12 and 12. 12 and 12, I made a mistake. Should be 24. I apologize. So I don't want this guy here. Indeed, the correct integral, that area is all combined to give me 24. Okay, just another example of finding the area between two curves. I had no other information, so I had to find where these curves intersected to get the bounds of integration, and then figure out which curve was the larger curve for a specific interval. Thanks for watching.